In the next video, we are going to talk about BGP peering, and here we are going to talk about the external and internal BGP peering sessions. We are going to examine in detail the neighbor formation. We are going to examine the different kinds of messages and keep alives that BGP sends. We are going to talk about the external BGP and the rules that govern the behavior of external BGP peering. We are going to talk about the behavior of BGP inside the AS, so we are going to talk about the IBGP as well. And finally, we are going to briefly touch upon the subject of scaling the IBGP sessions and scaling the capabilities of our internal BGP routing. Unlike pretty much any other routing protocol that either uses UDP for exchanging the information or uses its own IP protocol, BGP is actually just a TCP application. And it's a TCP application that actually operates on port 179. So port 179 is a well-known port used by BGP. So when BGP neighbors are configured, and let's say that we want to establish the BGP peering session between two of our neighbors, the first thing that needs to happen is this TCP session here needs to be established. Once the TCP, or the transport session, the control session as BGP calls it, has been established, BGP is going to start exchanging BGP messages to form an actual application relationship. BGP uses 4 messages: open, update, notification, and keep alive messages. Open message is used initially when peers are establishing the connection to send the locally configured parameters, like what is my own AS number, what are the values of certain timers, and so on. So this is the initial, hey, let's talk, let's peer message. The update message is the message that will either add routes to the routing table, to the BGP table on the remote host, or will instruct the host on the other side to no longer use certain routes. So if we are adding routes, we are going to have those routes with their attributes sent in the network layer reachability information, and if we want to remove them, they will be listed as the routes to be withdrawn. Notification message is used by BGP when an error condition is encountered. Now, keep in mind that the quotes error condition might be simply a neighbor signaling the other neighbor to cease the session. So it's perfectly normal to tell the other neighbor, hey, let's stop peering, but there is really no error condition. Or if any error condition is encountered, one neighbor will send a notification message to other neighbor, which is simply a de-peering message. It means, okay, let's stop this session. So we can think of open message is where the relationship begins, and the notification message is where the relationship between two routers end. In the meantime, if there are no updates to be sent or no notifications are being sent, the keep alive message are periodically going to be sent to signal the neighbor on the other side that this connection, that this TCP session is still alive. BGP is really using these keep alives as its own form of the hello protocol, which is used by so many different protocols. Now, the next thing that I would like to talk about is the BGP finite state machine. How does the BGP session form? What are the steps and processes that happen on the local router and between different neighbors when the session is being established? BGP finite state machine is a series of steps that every configured BGP router, sometimes called BGP speaker, needs to go through every time it attempts to establish a BGP relationship, a neighborship relationship, with another BGP speaker, with another BGP configured router. These steps are defined in the original BGP RFC, which is 1771. So in BGP 1771, you can see all these steps. I believe it's in section 8 of that RFC, but don't hold my word for it. The first step, the first stage of this finite state machine, where the whole process begins is the idle state. RFC specifies that in this state, all incoming BGP connections to port 179 should be refused, and that for this particular neighbor, no resources should be allocated, no system resources, that basically means memory, is being allocated for this particular neighbor. I should point out that in Cisco iOS, this idle state might be just a little bit misleading. When you do the command show IP BGP neighbor, you're going to see all sort of states that we have for that neighbor, what version of BGP we are running, what is the remote neighbor's IP address, how many messages we have sent, how many messages we received, and so on and so on. And at the very end of the output, we are going to see the state in which we are with this in relationship to this neighbor. Basically, we're going to see one of these states there. Sometimes you might see that the neighbor says idle when in fact iOS is behaving as if it was in either connect or actually in active states. What do I mean by that? What I mean by that is that you can see the neighbor that is actually in the idle state, but then there is a start event that happens. Now, what is the start event? It can be a large number of things. Start event could be you as the operator giving the router a particular command to start establishing the connection with the neighbor. Now, in iOS, there is no direct thing that is equivalent of this, but RFC says that there is such a thing as the start event. So maybe some other vendors have the ability for you as the operator to say, okay, I want to start establishing the connection with this neighbor right now. In iOS, the start event is really the connect timer expiring, which is an internal timer that you have very, very little control of. A connect timer expiring, and then the router is going to transition into either connect or active states. Or it could also mean that there was an incoming connection to port 179 from a configured neighbor, which in iOS is going to trigger the start event. And even though the router was in the idle state, it is actually listening on this port, so not all connections are being refused, and the router is going to transition into connect and later to active states. So what is happening in these connect or active states? Well, in connect state, the BGP engine is waiting for the TCP session to establish. We know that there is that three-way handshake, so there are certain things that need to happen before BGP can start operating. Once the operating system, the iOS, signals to the BGP process, again in iOS, that the connection, that the TCP session has been established, what is going to happen is the router is going to transition into the open sent state. Now, if the connect timer expires and there was some problem establishing the TCP session, it might have timed out, or there is maybe authentication problem or something, the router is going to transition into active state. Basically, in active state, the router is either actively initiating the sessions and is also listening for the incoming connections to arrive. So when you see active in BGP, when you are looking at the output of, say, show ibgp summary, active is usually not very good. It's a transient state. You really don't want your routers to be there for a very long time. But now let's say that actually there was a transition to open sent, that we actually did successfully form the TCP relationship. In open sent, that means that we have sent our open message, and you remember what the open message is, and we are now expecting to hear an open message from peer. Again, this is a transient state, and if this fails for whatever reason, the router is going to go to idle, and then it's going to start going through this process again. Now, if we actually have received an open message from our neighbor, we are going to move on to the open confirm state. Open confirm basically means that we have sent our own keep alive, and we are also expecting to see the keep alive from our neighbor. If you receive the keep alive, which is basically an acknowledgement of our own open message, just the same way our own keep alive was an acknowledgement for the neighbor's open statement. If you receive the keep alive message, the router is going to transition into the established state. This means that only the keep alives and updates are going to be exchanged, or notification messages if something is wrong. So really, this is a BGP finite state machine. This is how the neighbors are formed once we configure the neighbors. Let's see this in action. And to do that, what I'm going to do is I'm going to use the network that we already have. I have two routers, R1 and R2, that are directly connected on gigabit 1, and the network between them is 192.168.12.0/24.1 here, .2 here, and R1 is configured in AS65001 and R2 is configured in AS65234, and there is a direct peering between them on gigabit 1 configured. Now what I have done is I have shut both of these interfaces down on both R1 and R2, and what I'm going to do is I'm going to connect my Wireshark here, and we are going to tap into the communication between R1 and R2 as they are forming a relationship, and let's take a look at how that goes. I'm also going to be running some debugs on R1 to see all these states that I talked about as they are happening. So going to R1, what I'm going to do first is I'm going to say debug IPBGP, and then I'm going to specify the neighbor 192.168.12.2. So now I'm going to be seeing all events as they are happening in regard to the neighbor 192.168.12.2. Also, what I'm going to do is I'm going to go to my Wireshark. I'm going to start collecting the data here, but I'm interested only in seeing TCP or BGP traffic. If there is no other TCP traffic between them, this will only show me the BGP traffic as it is happening. Now, why am I saying TCP or BGP here? Well, if I said only BGP, I will see only the actual protocol as it is happening. So pretty much I'm going to see events starting with an open message. But before that happens, there needs to be that TCP session that forms. That's not, technically speaking, BGP protocol yet. BGP starts with an open message. There is nothing BGP about that TCP session prior to BGP sending its open message. And Wireshark knows that, and it's a good thing to see that actually, you know what, I'm going to start by just capturing the BGP traffic, and then I'm going to add the TCP so you can see that extra traffic. It actually makes more sense to do it that way. So what I'm going to do next, as you can see now, the debug has been enabled, and on R2, I'm going to say show IPBGP summary. Now, what we are seeing here is that neighbor 192.168.12.1, or R1, is in idle state. If I go to R1 and if I do the same thing, show IPBGP summary, I'm going to see here that the neighbor is also in idle state. So in this state here, there should be really no events going on. So let's go to R1 and let's say interface gigabit 1, and I'm going to say no shutdown. Let's see if this changes anything. Well, it won't change anything immediately. It's going to take some time for router to start sending messages. So we can see now that BGP is restarting. We can see here actually that we had an indication that the active open has failed. Why did active open fail when we were not even in the open state? Remember what I told you. This idle indicator here may be a little bit misleading in iOS. What is actually happening is that 192.168.12.1 is now attempting to connect to this network here, but because the interface is shut down on the other side, that is failing. So let's bring that interface up. Now, here in Wireshark, if I add just a TCP, actually I will not see it. Let's see if we can. No, we don't have any TCP traffic going on. And the reason why we don't have any TCP traffic going on is that we really don't have any ARP entries for 2 here. So R1 cannot really form this session, so it's not even sending the TCP packet. Let's bring this interface out of shutdown now. So at this moment here, let me you know what, I'm going to remove myself here so that you can see the full screen. Oh, there we go. Now something is happening here. And if we go to our Wireshark, we are going to see here that now we have the open message has been sent, we have keep alives and so on. But let me show you that other thing that I was talking about. So this is BGP or TCP. You see here before the TCP, before the first open message was actually sent and exchanged, there was an initiation of the communication. There was the TCP SYN was sent, then there was a SYN ACK, and then there was ACK. There is the three-way handshake right here, you can see it. So that was happening while the router was in the connect state. Once that has been completed, once that session has been established, the router has actually moved to open send, and this is where the open messages started sending. Now, incidentally, here it was 12.2 that was the first one to send the open message. We can see that because this is the source and this here is the destination. But here we can see the open message. So here is the open message from R1 to R2. So let's see what our debug told us there. I'm going to scroll. First of all, let me turn off the debugs. So I'm going to scroll up and let's take a look at what happened here. So let me see, where did I get the first indication in the debug? There it is. So here it says passive open to 192.168.12.1. Now, what that passive open means is really that it was R2's active act of initiation that is going to trigger the active event. And we can see here now that we are moving from idle to connect as the result of getting the peer from TCB. Now, TCB is an internal iOS indicator of the TCP sessions established by the router and to the router. It stands for Transmission Control Block. And you can see at iOS level, so I'm just going to show you that briefly, show TCP brief. You can see here the actual session between R2, and we can see that there was a random number in use here and that it was a well-known number on our side, which means that the TCP session actually formed in this direction. And we can see that from TCP perspective, this is how it is seen. So as far as TCP is concerned, this is in an established state. This is a TCB, this is a unique identifier inside iOS that identifies this TCP session at the operating system level. And if you wanted to destroy this session, not through BGP, but actually at the TCP level, you would run the command clear TCP TCB, and then you would enter this number, and iOS would kill and destroy this session. We are not going to do that now because we actually want to go through this debug a little bit here. So we can see here that it went from idle to connect, which is exactly what we expected. And then we can see that there are certain events here that happen. So setting open, delay, timer, whatever it is. So basically it means that we are going to wait for 6 seconds before we send our own delay. But before we send our own open. But in the meantime, we have actually received a message. It says here we received a message of type 1, which is really an open message. And then this is here where the open message gets decoded. It says here that it is in version 4. The hold down timer has been set to 180 seconds. It does have some options. Options are really additional capabilities that router is able to perform, like for example a route refresh or the outbound route filtering, or it could be the multi-address family, etc., etc. So all these capabilities are going to be decoded here, but that's not the most interesting thing that we are interested about. The next event that we are interested about or interested in is this bit here. Basically says that we are now sending our open. And here we can see that we have switched our state from connect to open send. Let me disappear here. So we can see here that we have went from connect state to the open sent. Why? Because we have sent our own open. Now, because we have actually received already, and there it is, we have received the open, we are immediately going to switch to open confirm state, because we are expecting to get the keep alives and we are sending our own keep alives. That event did happen, and here we can see that we have now switched to the established state. Now, one more thing that I would like to point out here, it says that our active open has failed. Well, it has failed because all this here was the result of an incoming session here. Our outgoing session is no longer needed, so we are basically saying here, okay, it did fail and we don't care about that. So that particular our attempt to establish the active connection has failed. And after this has happened, after we have established the session, after it has formed, if we take a look at show IP BGP summary now, what we are going to see here in the state, we are no longer going to see that it was, say, in idle or connect or open confirm. Good luck, by the way, catching those transient state here. The only one that you are most likely going to see is active, and that's when something is wrong. Now, when the actual BGP relationship is in an established state, when the finite state machine is in an established state, you're going to see the number of prefixes received from the other neighbor. Let's now take a look in our Wireshark how all these things look like. So what I'm going to do now is I'm going to just remove the TCP. I'm just going to leave the BGP in place. So here is the open message that triggered all of this stuff. We can see it came from 12.2. There it is. It came from 12.2 and went to 12.1. And here I have already opened the BGP thing. The important parts of the open message are what is the AS number of the transmitting host, and we know that this was R2 here, so we are going to see that this was 65234. We can see the hold down timer. We have already seen that in the debug, and we can see here what is the BGP router ID. Then there are optional parameters, and these optional parameters are really those capabilities that I mentioned, like, for example, the multi-protocol extension capability that's supporting multiple address families. We can see route refresh capability, and there are actually two of them differently identified. Then there is going to be some unknown capability, whatever that might be, could be something Cisco internal. And then we have the support for the 4-octet, the 32-bit AS numbers. So all these things here are seen in the open message. Here in the open message from R1 to R2, we pretty much have the same parameters. Then we have keep alive messages here that are being exchanged either on a regular schedule basis or as the result of confirming the open message. This is when we switched into the open confirm state. And finally here we can see that there were the update messages being sent. So we actually have some routes being exchanged. So here we can see loopback 2 of R2 being advertised, and we can see here that no routes are being withdrawn. So this is unfeasible routes length here. So, and we are going to see keep alive messages sent there. Keep alive is always sent as an acknowledgement to when we send the update, we respond back with the keep alive, and the keep alives are also periodically sent, which we can see here. So really, this was the BGP finite state machine. We are now going to start taking a look into BGP peering sessions and how they are different when the peering is external, that means between the neighbors that are not in the same AS, and the internal peering sessions. I'm going to start with the easier one, with the external BGP. For a peering to be considered an external BGP peering, what needs to be true is that the neighbors that are peering need to be in different autonomous systems. That means that if we had two routers, let's say our R1 and R2, when we configure the peering between them, if they are not in the same AS, like in our case we have 65,001 and 65,234, these two routers will be considering this peering here external peering. That means that the behavior they are going to exhibit on this peering session, the default behavior, the default policies, the requirements, they are going to be those of external peering session. So what are those peering rules? Neighbors should be directly connected. Now, please take note of should. This means that this is presumed default behavior, but it doesn't have to be this way. We can have external peering between neighbors that are not directly connected. However, if this is true, there are some configurations, some extra steps that need to be taken. First of all, we need to have some sort of an underlying reachability protocol. If the routers are not directly connected and we want to have peering between them, let's say that we wanted to peer between our R1 and R3 through this router, whatever it might be here, and we wanted to peer between these two, somehow this router here would have to know how to reach this router here, and this one will need to know how to reach this one here. But there is another situation in which we have BGP peering between non-directly connected neighbors. And while they may appear to be directly connected, let's say that we had two routers that we wanted to peer between the loopback interfaces here. These loopbacks here are not directly connected. These interfaces here are directly connected. So we can still have ebgp peering between these two routers, but they are not directly connected. This is not an uncommon setup, and it does have some dangers associated with it. This underlying reachability between these two loopbacks can be accomplished using static routing or using IGP. Well, in some advanced cases we can use BGP over BGP, but I'm not going to talk about that. That's not very common configuration. Now, if we have static routes here as an underlying routing protocol, there is really no danger. We are simply going to have a static route that is going to say that this loopback is reachable through this interface on this router here, and this is done. We are going to have the exact opposite on this router, and this is it. However, if we used an IGP as an underlying routing protocol to provide the reachability between these two loopbacks, we might have a problem if this same loopback ends up being advertised in BGP. Because remember, the admin distance of external BGP is 20, and this is lower than pretty much any of the IGPs. That means if we learn this loopback here in ebgp, we are going to prefer that route over an IGP learned one. Now, why would that be a problem? Well, to understand why that would be a problem, we need to take a look at what are the default policy behaviors in external BGP. What I mean by default policy behaviors is what is going to happen with the routes that we have learned, say, from internal neighbors, from other external neighbors. How are we going to process them? Where are we going to advertise them by default? And are we going to update and change any of the attributes by default? Most of these things can be changed, can be overridden by settings in either route maps or on direct neighbor sessions, and we talked about changing these attributes before, but this is the default behavior that I'm going to talk about. The first one, and the most important one, is the next hop attribute, and you might remember that this is probably the most important attribute in BGP, in a sense that if next hop is not reachable in the routing table, the routes are not considered to be the best, or cannot be considered to be the best. So why would, for example, this be an issue with this configuration here? Well, if we have the router here, and let's say that this is our R1 and R2, and we want to peer instead of direct connections, we wanted to peer between the loopbacks. And let's say that just for fun, we ran OSPF as an underlying protocol. What we are going to do here, we are going to advertise the loopback of R2 in OSPF, and R1 will learn it with the admin distance of 110, which is fine. Now, when this loopback here gets advertised in ebgp, this is going to be now learned here with the admin distance of 20. So this route will disappear from the routing table, and this one here goes into the routing table. So what does that actually mean? Well, that means that we're going to have the route that this loopback here is reachable with the next hop of R2. But what is going to be the next hop? Well, it is set by the advertising router, and by default, unless we change it in any way, it will be whatever is the peering address, whatever is the update source. And the update source on our ebgp peering is the loopback itself. So we are going to have information that loopback is reachable through the loopback, which if we recursively look up is going to be reachable through this. So we are basically going to have a local routing resolution problem on R1. The problem that is commonly called as recursive routing, that a route is reachable through itself. In other words, what we are going to end up with is a valid route in the routing table, which is going to satisfy the requirement of a valid reachable next hop. However, it is not actually reachable by traffic because it leads back to itself. So in effect, the peering session between R1 and R2 is going to become ineffective. Now, given the default hold timer of 180 seconds in iOS, this means that this BGP session here is going to remain up for 3 minutes before routers notice a problem. Then after 3 minutes, this peering session is going to go down, this route is going to disappear from the routing table, and this one is going to make a comeback. When this route comes back, R1 and R2 can communicate, the BGP session forms again, the ebgp route gets advertised, and the same problem repeats itself. Now, I know that this might be a little bit too much to understand just on this imitation whiteboard, so let's take a look at this one actually in iOS. I want to show you this particular issue. For that purpose, I'm going to use two different routers. I'm going to use my R5 and R6. And they're going to be interconnected on gigabit interface 3, and the network between them is going to be 192.168.56.0/24, and I'm going to have .5 here and .6 here. I will have a loopback on R5 and R6, and the address here will be 192.168.0.5/32, and on this side I will have 10.0.0.6/32. I want to run a routing protocol between R5 and R6 and advertise these loopbacks into this routing protocol. And I think that the easiest and the fastest one to run would be EIGRP. So I'll run EIGRP 56 between them. And just for fun, I'm going to configure it using the new named mode because that's where things are going. And then we are going to establish ebgp peering session between them. So what I'm going to have here is my R5 here is going to be in AS 65,005, and my R6 will be in 65,006. So I want to establish the peering session, the external BGP peering session between these two loopbacks. So let's head to the terminal and take a look at this. And you know me by now, I'm not going to start configuring anything unless I have the connectivity. So I'm going to first start from R5. I'm just going to say show IP route connected. What I'm looking for here is the 56 network, and what I want to do is I want to be able to ping 56.6 on that network, and it seems that that was a success. So on R6, show IP route connected, I want to make sure that I can ping 56.5, and I can also observe that I do have loopback configured on R6 and that I have the correct address there. And I can see pretty much the same thing on R5. There is a loopback and it's 192.168.0.5. Now let's configure EIGRP. So the first thing that I'm going to do here is router EIGRP. And I'm going to give it some name, and let's call it by our AS number. So it's going to be 65,005, and here I'm going to say address family IPv4 autonomous system, and I have to share the autonomous system between R5 and R6 for EIGRP. I'm going to make sure that there is no, actually it's configured elsewhere in this case. So I'm just going to make sure that I don't create auto summary, and just a quick reminder here. So this is going to be in topology base, and I'm going to say no auto summary here, and then I'm going to say network 192.168.56.0. So I want to configure it there, and I want to make sure to advertise my loopback into the EIGRP. So if I do show IP EIGRP interfaces, this is what I want to be seeing. Now if I do show run section router EIGRP, this is pretty much what I can copy paste to the other side. So I'm just going to do this one here. Then I'm going to copy paste this. Actually, topology base, just going to make sure that no auto summary is configured. Going to run this network here and network 10.0.0.0.6 0.0.0.0, and I can see that the neighbor is already up. So if I go to R5, show IP route EIGRP, I should be seeing the loopback of R6, and on R6, show IP route EIGRP, I should be seeing the loopback of R5. So if I ping R5 with the loopback of 0 as source from R6, I should be getting the responses. And the same thing here, source loopback 0, I'm getting the responses. So I do have my EIGRP ready now, so let's build BGP. I'm going to start with R5. On R5, I'm going to say router BGP 65.5. This is what our AS number is. I'm going to set the BGP router ID to be 192.168.0.5. This is optional, I don't have to do it. I'm also going to say BGP upgrade CLI, because this is what I like to do. And I'm going to say neighbor 192.168, actually it's neighbor 10.0.0.0.6, remote AS 65,006. And here what I need to do is, I need to say that I want to send my open messages from the loopback interface, and I want the TCP session to be formed from the loopback interface. Now, by default, because there is that requirement that external neighbors are going to be directly connected, what is going to happen here, these messages are not going to be sent out. They are not going to be sent out because BGP expects to have a directly connected neighbor. In this case, our neighbor is not directly connected because the peering will be between the loopbacks. Now, because R5 and R6 for that matter will expect directly connected neighbors, this message or this TCP session will be attempted to be established with the TTL set to 1 on the IP packets. Now, if the TTL is set to 1, it will never reach R6 because it needs to go from loopback to this interface, and TTL will be decremented at that point. So we cannot send the packet with TTL 0. R5 knows this, so it's not even going to attempt. Now we can change the behavior of this TTL and we can relax it. We can set it to 2, 3, 5 or whatever, or we can simply set it to 255 and tell R5 establish the session with R6 any way you know. And this is something that we can do if we simply say ebgp multi-hop here on the neighbor statement. We can specify what our hop count is going to be. If we don't specify it, it will be 255. So now if I do show IPBGP summary, I'm going to see that the neighbors are idle at the moment, but very, very soon we might actually see this change state to active. But while we are waiting for that, let's go and configure R6. Again, I'm going to do a little bit of copy pasting here. What I can do is, well, I don't have much to copy paste, so let's start from scratch. So here I'm going to say router BGP 65.6, and I'm going to say BGP router ID 10.0.0.6, and I'm going to say BGP upgrade CLI because I like the new format, and I'm going to say neighbor 192.168.0.5 remote AS 65.5 update source loopback 0, and we are also going to say ebgp multi-hop here. And we can see here that the neighbor is coming up. Oh, actually it's not coming up, it says it's in a wrong AS. Oh my goodness, what did I do wrong? Let's see. Show run section router BGP 6505. Oh yes, I have configured here the neighbor to be in my own AS, so I'm trying to configure this as an internal session. But you know what? I honestly made this mistake, but it's actually not that bad that I made a mistake. If you make a mistake like this, this is what you can expect. You can see that iOS is very, very loud about that thing. Now, one thing that I want to show you here is this error message here. Now, with this error message here, we are telling our neighbor that, hey, you are in the wrong AS. I'm not expecting you here. Now, with this message here, we can decode what the neighbor was configured to be in. So let Let me show you how you can do that. So what I'm going to do here is I'm going to see to start my calculator. Let me just find it because I don't often use it. There we go. Here's my calculator. And I'm going to switch it to programmer mode in this case. And this number here, these letters F, D, E, E, these are actually hex numbers of the AS. So if I confirm this here, if I change this to 10, I can see here that I'm telling the neighbor, hey, I can see you configured in 6506. Now let's see what is happening on our 6 side. Here we are also sending the notification. Did I make mistake on both sides? This would be silly. No, I did not. So here somewhere we should actually be seeing slightly different error message. Let me see if maybe it's somewhere down. I'm not seeing it. Let me see that configuration again. I want to see the section router BGP. So this one's 6505, this one's 6505. So yes, exactly, that's what I'm seeing. So here, apologies. So on R5, we have configured R6 as if it was in 65,005. So I just misread that message there. Now R6, on the other hand, was configured properly to be in 65,006. So what we are seeing here with this error message is we are telling the neighbor, hey, you are configured in the wrong AS, and this is the AS I am seeing from you. The router is basically, with this log message, telling us as the operator that we may have misconfigured the neighbor's AS, which is exactly what I've done. This is an incorrect configuration. This should be 65,006. So let's go ahead and fix it. So I'm going to go into this router BGP. I'm going to remove this neighbor. I'm going to add it back now with the correct AS, and I'm simply going to copy paste these two, because when you remove this command, when you remove the neighbor AS command, what is going to happen? You're going to remove all the related configuration for that neighbor, because remember, this is a mandatory command. You cannot have the neighbor without defining the remote AS. Let me show you that as well. So what I'm going to do now is I'm going to remove this neighbor. So I have removed the configuration, and I'm simply going to repeat, for example, this command. I want to say neighbor update source loopback 0. Look, it's telling me that I cannot configure this command because I have not defined the neighbor with the remote AS. And if I take a look at my BGP configuration, there it is, it's all gone. So what I need to do here is I first need to specify the neighbor in the remote AS, and then I can run the other commands, like the update source and like the ebgp multi-hop. There it is. So now if I repeat my show run, I'm going to see the correct thing. And BGP, I can see here, it just came up. Now, if I do show IP BGP summary, what I'm going to be seeing here is that 0 prefixes have been received. That's okay, because we have not advertised anything. At this moment, what I can do is I can ping loopback 6 from the loopback of R6 from the loopback of R5. Now, I'm going to go to R6, and I'm going to go to router BGP 65,006, address family IPv4, and I'm going to say network 10.0.0.6 mask. I'm going to advertise the loopback of R6 into BGP. Now, at this point, if I do show IP route on R5, there we go. We can see now that the route that I have in a routing table for 10.0.0.6 is now BGP route. Please observe that it has the administrative distance of 20 and that it is reachable through 10.0.0.6. which in turn is reachable through 10.0.0.6. So now I have recreated my recursive routing problem. At this point, from R5, I cannot ping R6. If I don't use the source loopback 0, I still cannot ping it, because the source doesn't matter. Now, keep in mind that technically speaking, at this point, R6 can communicate with R5. It's R5 that cannot communicate with R6. at this moment, if I do show IP BGP summary, I'm going to see that everything is okay. Well, not everything is okay, because this timer here will never, at this moment, go beyond 3 minutes. Why? Because at the 3-minute mark, which is about 1 minute away from now, it is going to go down because, well, not maybe at the 3-minute mark, actually, we have to know when the keep alive stopped. But at the moment the keep alive stopped, we have to wait 3 minutes from that. That means since the moment R5 learned that BGP route, the 3 minutes after that, roughly, this session is going to go down. Now, when it reestablishes itself, we are going to see this timer here never go above 3 minutes. Because when 3 minutes expire, R5 and R6 will not be able to communicate anymore. And when that happens, the BGP session is going to go down. When BGP session goes down, the EIGRP route will show up, and when EIGRP route takes over, the BGP session will reestablish, the route will be advertised, and the session will go down after 3 minutes. So what I'm going to do now is I'm going to wait for the BGP session to go down, and I'm going to, at that moment, run show IP route to show you what is happening with the routing table. I might need to do it multiple times. So right now, we're just going to wait for this to happen. I might fast forward a little bit. Oh, I don't have to. There we go. Look what happened. The BGP session went down, and we can see EIGRP route in the routing table then. Now we can see that the neighbor came up, and if I do show IP route, I can see here that the BGP route is in place. Show IP BGP summary now shows me this timer here at 10 seconds. That means that there was a change 10 seconds ago. 3 minutes from this 10 seconds ago, the BGP session is going to go down. So let's analyze what happened here. The keep alive, or here we see that the hold time expired. That means 180 seconds went by without receiving a keep alive message. Now, we are tearing down the session, and at this moment, if I scroll down in this output, I'm going to see that now route to 10006 becomes EIGRP route with the admin distance of 90. At this moment, R5 and R6 can communicate, which means that they are going to reform the session back up. When this happens, the BGP route is going to get advertised and take over. At this moment, there is no reachability between R5 and R6. And this up-down timer is now at 1 minute and 11 seconds. So what I'm going to do now is I'm going to wait for about 2 minutes. We have about 1.5 minutes to go. And almost on the cue there, the neighbor went down, it closed the session. Now the EIGRP route is being relearned, and here we go. The neighbor is back up. Now, this is obviously a problem. So how do we fix this problem? Well, think about it. Don't think in terms of commands that you may need to run to fix this. Think in terms, what do we need to do here? Well, what we need to do here is, when we go and take a look at our routing table on R5, what we need to make sure is that R5 will always prefer EIGRP route for this loopback over the BGP learned one. So how can we do that? Well, we need to either lower the admin distance of this route or increase the admin distance of this route, or use a built-in mechanism in BGP that is actually meant to solve this particular problem. Now, what is that mechanism? It is something called the backdoor route. The command is very simple. It's configured on R5, and it's configured as a network statement. So we are going to say network, and then specify the loopback of R6, 10.0.0.6, mask 255, 255, 255, 255. Now, if I press enter at the moment that I'm typing this command in, what's going to happen? R5 is going to attempt to advertise this into BGP, but I'm not going to press enter. I'm actually going to use a backdoor keyword here. Now, what this keyword does, what this keyword will do actually, is the following. It is going to tell R5, if you receive this network here, that matches this network and this mask exactly, treat it as a backdoor link, which means do not give it the usual admin distance of 20, and instead give it the admin distance of 200, the same that would be given for locally generated routes. Now, locally generated routes by default in iOS have the same admin distance as those routes learned from internal peers. Now, 200 is higher than 90. It is actually higher than all the IGPs. Hence, the whole idea of having internal BGP routes having higher admin distance, which means that on R5, the route learned from BGP, from external BGP, which would by default have admin distance of 20, is now no longer going to be preferred over an EIGRP route. Let me show you that. So going into my terminal, I'm going to go to router R5, router BGP 65005, address family, IPv4. Remember, all policy settings are done inside the address family, and this is a policy setting. So I'm going to say network 10.0.0.6 mask, and here if I do the question mark, there is my backdoor option there. So I'm going to say backdoor. Now if I do show IP route, I'm going to see that EIGRP route is still in the routing table. No matter how many times I repeat this, show IP route, show IP route, show IP route, show IP route, there it is. Now it stays. If I do show IP BGP, what I am going to see now is that this route 10.0.0.6 has this lowercase r with it. Now, lowercase r is identified here in the output as the RIB failure. Now, when you read the word failure, you are immediately going to a full panic mode. Oh my God, what has failed here? Well, nothing has really failed. What RIB failure indicates is that this, as far as BGP is concerned, is a valid route. It is also, in this case, the best route. We can see that this greater than sign here marks that this is the best route we have for this prefix, as far as BGP is concerned. However, RIB failure here indicates to us that there is a better route from another routing source, from another routing protocol, that has won the insertion into the routing table war, so to speak. So, what has won? It was the EIGRP route that is now winning over this external BGP route. Going back to our default policy behavior here, I would like to note that in external BGP, the primary loop prevention mechanism is the AS path contents. The way it works is if an external router, if the BGP speaker receives the route from an external neighbor, it is going to examine the contents of the AS path, and it's going to examine the contents of both the AS sequence and AS set attributes, and it's going to look for its own AS number in that AS path. If it encounters its own autonomous system number in that, in either one of these two attributes, it is going to reject the incoming update. This simply means that the route from one AS traveled to some other AS and is now trying to make the comeback into this AS. Depending on the iOS version, this might actually happen on this peering session here. Some of the older versions of iOS, when they received a BGP update from the neighbor, they would also send this update back to the same neighbor. This doesn't happen with all the versions of the iOS, and in the latest versions of the iOS, from what I have seen, this behavior has been removed, but be on a lookout for it. There is nothing bad about this being re-advertised. It's a little bit of a wasteful behavior from the perspective of the bandwidth and the time it will take to converge this BGP peering session, but BGP does that by default in some of the older versions of the iOS. Now, all other routes that have been accepted, that means that exist in the BGP table as valid and best routes, so only the best routes are advertised, will be advertised on the external peering session. And as they are being advertised, the next hop is going to be changed and set to whatever is the update source on that peering session. As you can see, external BGP is really not that complex. It's relatively straightforward. Internal BGP, on the other hand, is a much different story. And now we are going to talk about the internal BGP, and I'm going to talk about two things there. I'm going to talk about the rules and the default policies that exist in the internal peering sessions, and then we are going to talk about how we can scale our internal BGP to address the issues that arise from certain rules that govern the behavior of the internal BGP. And there I'm going to talk about route reflectors and the BGP confederations. Let's now take a look at the peering behavior of internal BGP. The first thing is, what makes the peering an internal? If the neighbor being defined is defined with the same autonomous system as our own from the perspective of the peering router, this peering session will be considered to be an internal and must follow the internal BGP rules. Now, the first rule here is, or I wouldn't say a rule, but kind of the first difference between internal and external BGP is that unlike the external BGP, where by default all our peers need to be directly connected and we can override that behavior, with the internal BGP, there is no such restriction. The neighbors don't have to be directly connected. The reason there is that the assumption is that there is an underlying connectivity between the neighbors. Now, they may be directly connected. There is no restriction against that. But if there is no connectivity, if they are not directly connected, we need to have an underlying IGP. And in internal BGP, in ibgp, the assumption is that yes, there is such a protocol running inside the autonomous system, unlike the external, where the assumption is that the BGP is the only protocol running. So the neighbors may not be directly connected, and there is really nothing special that needs to be done. In fact, with the internal BGP, the most common configuration is to actually have the peering done between the loopbacks, because that way if we have multiple paths between, let's say, our neighbor 1 and neighbor 2 here, so we have these 3 paths here and we also have this path here, no matter which one of these interfaces is up and running, as long as we have a connection between our loopbacks, our peering session will be operational and will be up and running. So this is the first thing. The second thing is, obviously, we're going to talk about the default policy behavior. Unlike ebgp, where next hop is changed when the routes are being advertised, in internal BGP, this is not the case. And this may actually lead to some interesting scenarios. So let's take a look at one of these possible scenarios. Let's say that we had 3 routers. And let's say that these 3 routers were actually in 2 different autonomous systems. So this is going to be our autonomous system 65001, and let's say that this is going to be 65234. And you might be guessing already that this is something that I already have up and running. So here, let's say that we do have a peering between directly connected interfaces. And as a quick reminder, this in our scenarios here is gigabit 1 interface, and let's say that the network here is 192.168.12.0/24, and we want to have a peering session between directly connected interfaces. This is good. Now let's say that here on our 2 and 3 we did have loopback interfaces, and they are going to be 192.168.02/32, and this here is going to be 192.168.03/32, and let's say that interface here is gigabit 2, and I'm going to be using sub-interfaces in this scenario. So gigabit 2, 23, and the network here is going to be 192.168.23.0/24. So let's say that I wanted to build an internal BGP session here. So I want to build ibgp session between R2 and R3. That means that I need to have some underlying protocol so that this loopback here can actually be able to reach this loopback here. So let's run EIGRP. So I'm going to run EIGRP23 on these interfaces, and I'm going to advertise the loopbacks into this EIGRP23. If I build this correctly, and if I build this BGP neighbor here, let's examine what is going to happen with the BGP update as it arrives from R1. Now, you might remember that on R1 we have some loopback interface here, and if I'm not much mistaken, it's 172.16.01/32. So we are going to advertise this in BGP. Now, when this arrives to R2, the next hop of this route will be set by R1 to be whatever is the update source for this peering. And in this particular case, it will be this interface here. So from R2's perspective, this is an external route. External routes will be advertised to internal peers. So now this gets advertised to R3. But mind you, this is an IBGP session now. And in IBGP session, the next hop does not change. So when this route arrives to R3, it will have the next hop attribute of 192.168.12.1. Now, unless I run EIGRP on this link here, or unless I redistribute this in here, this route is now going to be ineligible to become the best route on R3. And I might need to do something on either R2 or R3 to fix this. Let me show you this. What I have configured at this moment is the peering session between R1 and R2. I also have the connection between R2 and R3, and there is EIGRP running between them. So let's take a look at that. So if I do show IP route connected on R2, I'm going to see that I do have network 192.168.23.0/24, and it's basically right here. It's this line here, second from the bottom, that we are looking at, and I can ping 192.168.23.3, so I have the direct connectivity. And if I do show IP route EIGRP, I can see that I have the loopback in my routing table. If I ping 192.168.0.3 source loopback 0, I do have connectivity from loopback to loopback. On R3, if I do show IP route connected, I see that I have my 23 network. If I do show IP route EIGRP, I can see that I have the loopback of R2, and I should be able to ping it, and that is successful. So on R2, here is my configuration here. So I do have my router BGP, and whenever you're configuring BGP, it's a very good idea to actually use a notepad or some text editor to actually edit this configuration, because what you're going to have is mostly the same configuration on other sides. So what I'm going to do here is I'm simply going to copy paste whatever I had on my R2, and what I'm going to do now is I'm going to change the configuration to remove unnecessary stuff, and I'm just going to put in the configuration as I want to have it. So I'm going to have the peering from R3 to R2 between the loopbacks. So what I want to do here is I want to set the update source loopback 0, and this is an external session, so really nothing else needs to be done. I may want to activate it here, but there is really no need to do that because all IPv4 sessions will be activated by default. So I'm going to go here and say copy paste, and now really what I need to do is I need to repeat pretty much the same configuration on R2 itself. And there you go. You see, copy paste with a little bit of editing, and now I'm going to have my BGP peering session come up. I am expecting to see it in just a minute there. Oh, actually, I did make a mistake. Yeah, I made a mistake again. This is the wrong AS. So let's fix this then. So I'm going to say no this, and I'm going to say this is neighbor 234. Much better now. And going to fix this. Okay, maybe I need to copy paste this one more time. There was this tiny little error message here. So let's do the same thing on the other side. And actually there is an easier way to do that. So I'm just going to do this, and do not do this in production environment. You can do when you're studying, but removing the BGP process is not actually a good idea to do. So now let's see if our neighbor, now it's much better. Now we can see that the neighbor came up here. Everyone makes mistakes, but it's important that if you make a mistake, a silly mistake like I did, it was a wrong copy paste. I used the wrong AS number because I copied the configuration for R1 as it was configured on R2 to R3, and that made me use the wrong AS. Now, the reason why I didn't get any error messages here is because I did use update source loopback, and the neighbor wasn't directly connected, so the router wasn't even trying to send the TCP, to activate the TCP connection, so there was no SYNs sent, and because of the TTL expiry. I did talk about that a little bit earlier. So this is why we didn't have that error message with the peer in the wrong AS. Now, if we did configure the update source and ebgp multi-hop, in that case you would have gotten the error message, but we don't need ebgp multi-hop because this is an internal session. So now on R3, if I do show IP BGP summary, I'm going to see that from R2 we are actually learning two prefixes. Now, if I take a look at show IP BGP, I'm going to see that one of these prefixes has a rib failure, and as we remember, the rib failure isn't actually that big of a problem. And we do have a rib failure for the loopback of R2, which is perfectly legitimate because we are actually learning it from EIGRP. Rib failure is what we want to see in this case. However, this network here is much more interesting. This is the loopback of R1, and we can see here that as far as BGP is concerned, it's a valid route. Now, what valid means is, yeah, we received it, it's okay, all the attributes are there, there's nothing wrong with this route. But what is missing is that this is the best route as far as BGP is concerned. So why is it not the best route? It is the only route for this prefix in our BGP table. So why isn't it the best? We cannot tell that from this output here, but what we can do is show BGP 172.16.01, and what we are going to see here is this. It says it's inaccessible. What is inaccessible? Well, we need to look at this bit here. This is the next hop for our route. Now, going back here to our whiteboard, this here is, this address here is 192.168.12.1. Now, we know when this route was advertised to R2 that this was set to be the next hop by R1. Now, when R2 re-advertised this route to R3, because of the rules in in IBGP, where the next hop is not changed when routes are advertised, this next hop remains on R3. Now, because we have not advertised this network here into our EIGRP, or because we didn't redistribute it, R3 now receives the BGP route, a valid BGP route, with the next hop that it doesn't have in a routing table. So if we go here and if we do show IP route, oops, made a mistake, copy pasted again. So show IP BGP 172.16.01, let's repeat the process. So if I do show IP route this, I will see that the network is not in table. If I do show IP route, indeed, the network is not in table. So how can I fix this problem? Well, I have multiple possible solutions here. One is I could advertise this network in EIGRP. Two, I could advertise this using the network statement in EIGRP, and I could make the interface passive just to avoid speaking EIGRP with R1, or I could redistribute this network, or I could go to R2, and this is probably the most elegant solution. I would go to router BGP, so I'm going to go to router BGP. I'm going to go into the address family IPv4, if I'm using address families. If not, you don't have to go there. And then I'm going to say neighbor, and remember, this is a policy we are setting, 192.168.03, and I'm going to say next hop self. Now, what this command is going to do is when R2 advertises the route to its internal peer, it is going to set the next hop to be whatever is the update source for that peering session. In other words, configuring the next hop selves makes IGP behave from the perspective of the next hop behave in the exact same way as ebgp does. When we advertise the route, change the next hop from whatever it was to ourselves. So if I now go to my terminal to R3, if I do show IP BGP 172.16.01, Now I will see that my next hop is 192.168.0.2, and here we can see what is the IGP metric for this. And remember, this is used in the best path selection process at about step number 8, I believe. With 9 we have all those bunch of tiebreakers. We can also we can also see here that this was our peer address. So right now we can see that this here is the same value. So at this point, if I do show IP route, what I am going to see here is this route learned from BGP. So now this route is actually valid and best. And if I see this shorthand output of show IP BGP, I can see that this route is valid, which it was before, but I can also see it is the best route. One more thing that I would like to show you here. Let's go all the way back to R1. So on R1, if I do show IP BGP, what I want to take a look at here is the route 172.16.0.1. Now, taking a look at this route, and let's say that you are seeing this for the first time, what could you tell me about this route? Is it an internal route or is it an external route? Did we learn it from someone else or did we inject it ourselves? Let me answer that. First things first, this route looks like it might be an external route. Why? Because I'm looking at this part of the output. If in this part of the output I see a lowercase I, this will indicate that this is an internal route. So this route, as far as this router is concerned, is not an internal route. But did we learn it from someone else? Well, we have two cues that might tell us that this is not the case. First cue is the weight of 32,768, which we know will be by default for locally generated routes. The second cue, if this was an external route, we would have an AS path here. We don't have an AS path. Please don't mistake this lowercase I for the AS path. It is not. This here is an indicator of the origin code of IGP. Now, keep in mind, lowercase I here indicates an internal route. Lowercase I at the end indicates the origin code of the route. So this is the second cue. The next cue, or the next clue, is really the next hop of 0000. So if we have the next hop of 00000, and if we have the route that appears to be external route, and we have the weight of 32,768, and we don't have the external path, we can be fairly certain that this is a locally injected route. Now, let's take a look at this same route on R2. So I'm going to say show IP BGP. Now, let's take a look at this route. Again, I'm looking at the output here. There is no lowercase I, so this does appear to be an external route. I can see that the weight is 0, which probably means this is not that this is not a locally injected route. Second, or the third, is the AS path. It's non-zero. And finally, the next hop is not all zeros. So all these indicators here tell me that this might be an external route. Now, we know it is an external route because we know how our topology looks like. So we have R2 and we have R3 here. So this is the AS boundary here. So when this route was learned here, it was an external route. Now, what about the route here? Will it be perceived as an internal or external route at this stage here? What do you think? Well, if your answer was it was an external route, you are in for a surprise because it is not an external route. This is now perceived, sorry about that, this is now perceived as an internal route. We can see here, we have a lowercase I here. This means it's an internal route. Keep in mind, this I is irrelevant. It's simply an origin code. This one here tells us it's an internal route. So how can it be an internal route when it comes from a different AS? The differentiation between the internal and the external routes doesn't mean where the route originated in, and I did talk about this earlier. It means where did we learn the route from? So in our case here we have R1, R2, and R3, right? This is the AS boundary. when R2 learns this route, it's an external route because it was learned from an external peer. But when R3 learns this route, it learned it from an internal peer. So here on R3, this route will be perceived as an internal route. So R3 now has the route that it learned from an internal peer. So from the perspective of R3, this is an internal route. Now, why is that important thing? Because routes learned from other internal peers are not advertised to other internal peers. So here I forgot to mention, so it says routes learned from internal peers are not advertised to internal peers. Which means that if here on R3 we had another router here, let's say R4, this route would not be advertised to it. But if on R3 we had another, let's say R5 here, which was in a different AS, this route, yes, would be advertised to the external peer, but it will not be advertised to internal peers. And the reason for that is the loop prevention mechanism that I talked about earlier. So how do we work around this? There are multiple ways we can do that. The first one is to use a full mesh of peering sessions here to solve the problem. Now, what is the full mesh of peering sessions? Now, you will remember that there is no requirement that IBGP peers are directly connected to each other. Because we don't have that requirement, what we can do here is, let's say we have our R1, R2, R3, and let's say that we add our R4, which we are going to do in a minute. What we can do is we can have the peering between the loopbacks here between R2 and R3. Then we can have the peering between R3 and R4, and we can have the peering between 2 and 4 in this case. And all these peerings can be done between the loopbacks. Now you might be thinking, if R3 here is not going to advertise the route to R4, what is the point of this peering session? Well, what if R4 had a connection to some router that is outside the AS, so yet another AS boundary here? How would then R3 learn about these routes here? Well, over this peering session that is right here. So this is why we have to have the full mesh of peerings to actually work around what I like to call IBGP split horizon. It is of course not officially called split horizon. I like to call it split horizon because it really behaves in such a way. If we take a look at the routes received from one internal neighbor, then we are receiving them on this internal neighbor. We are not going to advertise them back to internal neighbor. So it kind of does behave like a split horizon. And it's very, very easy to understand it if we use a term that we know and understand from different protocols. So one of the workarounds for this split horizon problem, as I said, is the full mesh. And in this case here, full mesh is actually not that bad of a solution. But the problem is, if we had a larger autonomous system, full mesh won't scale. It won't scale because it requires n times n minus 1 over 2 number of peering sessions. And what would happen if your internal autonomous system here said, let's say 5,000 peers? How many peering sessions would that be? Let me answer that question. A lot of peering sessions. So the full mesh here, even though it solves the problem in a relatively small AS like this one here, wouldn't scale to larger autonomous systems. So for that reason, I'm going to skip using full mesh as the solution here. What I'm going to do now is I am going to add R4 to our mix without the R5 here on this side. So I'm just going to have R4, and I'm going to have it connected directly to R3, and the network that I'm going to be using there is going to be 192.168.34.0/24, and I'm going to peer between the loopbacks, and this is going to be interface gigabit 2.34 on both of these sides. So that should make things simple. So let's head to the terminal, configure this. I already have EIGRP pre-configured, so I'm just going to add BGP, and let's see both the problem and the possible solution for the problem that's going to come up in action. I am of course going to start that by making sure that my R3 and R4 are actually connected. So on R3, show IP route connected, what I'm looking for here is the network 192.168.34/24, and indeed here is my network. It is connected on the gigabit interface right where I want it to be. And I'm going to do show IP route EIGRP just to make sure that my EIGRP has received the route from R4, and here is that route. So what I'm going to do now is ping 192.168.04 source loopback 0, and that works. On R4, similar verification. I have the EIGRP route. Show IP route, well, if I have the EIGRP route, I obviously have the connected route. So let's just try to ping between 4 and 3. I can do that. And just for fun, I'm just going to make sure that from R4, I can actually ping all the way to R2. And that also worked. Now let's configure BGP. So to do that, I'm going to use the configuration from R3, but I'm not going to make the mistake that I did before. So what I'm going to do now is going to bring in my text editor here. Let's make it a little bit wider here. And I'm going to make sure that this peering here goes to R3. So this looks good for the configuration on R4. So I'm going to paste this in. And for the configuration on R3, what I actually want to do is this, and that would pretty much be it. So let's paste this in. And now I'm going to wait for the BGP to come up, and I can see it actually did come up right here. So let's now make sure and see that the behavior I explained did happen. So on R3 here, if I do show IP BGP, I'm going to be seeing the route 172.16.01, and here is this route there, and this is going to pop out again, so let's put it back in. So here is the route that I'm looking for, so 172.16.01/32, and we can see it is actually an internal route. Now, going to R4, if I do show IP BGP summary, so the first thing that I want to see is that I am not actually receiving any prefixes here. Why am I not receiving any prefixes? Well, because all of them on R3, if I take a look at this output here, all of them have been internal prefixes. Now, if I have internal prefixes and R4 is my internal neighbor, that means that I am not going to advertise any of these prefixes. And if I go to R4, I'm just going to confirm that. Show IP BGP shows me nothing. How do I then fix this? Well, we said that we can have the full mesh peering between R2 and R4, and that would somewhat address this issue. But what I actually want to do now is I want to make sure that R3 advertises this route to R4. I want to make R3 kind of relax the rules of the route, of advertising the internal routes to other internal peers, because this may help me with the scaling of internal peering. Let's see how we can do that. One way would be to make our router R3 so-called BGP route reflector. Now, what is a BGP route reflector? Practically speaking, it's the router that has somewhat relaxed split horizon rules that allows the internal routes to be advertised to other internal peers. But not all internal peers, from the perspective of this route reflector, are the same. So let's take a look at some of the terminology that BGP uses to describe the behavior of route reflectors. The first thing, obviously, we are going to take a look at what the route reflector is. It's the router that has this feature enabled, that has this relaxation in place. This is configured on per neighbor basis. So when we have one router that, let's say, has multiple internal peers, so let's say that this is R1, that this is R2, and that this is R3 here. Now, R2 might be configured to perform route reflection with R3 or towards R3. That router R3 here is what we call a route reflector client. But this other router here that was on the left side of the connection, that one might be a non-client. So what is a client and what is a non-client? Well, route reflector client is the router that peers with the route reflector and for which the route reflector actually has the route reflection enabled. Route reflection is another way of saying we are going to reflect the internal route. Because think about it. Let's say that we have an external peering here. So this is an external peering. And then we have an internal peering, and then we have another internal peering. If we receive an internal route here, what we really want to do is to reflect this route to this router here. So this is why it's really called a reflector. It could have been called a route bouncer as well, but it is called a route reflector. Now, this word to reflect, or the purpose of this router here, it's very, very important to kind of get to the bottom of that word. It means that this route, as it was received, it will be announced here pretty much the same way it was received. Now, we can obviously apply some of the outbound policies here, but by default, this route is going to be sent completely unchanged, which means that whatever was the next hop advertised by this router here, it will be unchanged when it is reflected. Depending on the iOS version, even configuring next hop self on the client session here may have zero effect, because route reflectors are really not supposed to change the next hop of the route. So keep that in mind. By default, this will not change. So this router here better know how to reach this router here, which shouldn't be a problem because these three routers here should be running the common IGP. But if they don't, you might have a problem when you reflect the routes. And keep in mind that setting the next hop self on that peering session may be a little bit ineffective. So what is a non-client then? A non-client is an internal peer of the route reflector for which this feature has not been enabled. So why would we have that? Well, we could have a scenario in which we just have one client that we don't have a full mesh with, and there is no need to enable route reflection for every single router in the network, when enabling it for that one router will and should be more than enough. Now, let's take a look at some of the route reflection rules. So what I'm going to do now is I'm going to come up with a scenario. So let's say that I have 4 routers here that are in some AS, and then I have these, let's say, 5 routers here. So I'm going to hide myself now, that are all in, let's say, AS 100. So this router here is going to be our route reflector. And let's say that we have peering sessions that follow these black lines like this. So route reflector has some internal peerings. Let's say that this is external 1, external 2, external 3, external 4. So there are some external peerings going on here, and we have a bunch of internal ones. Now let's say that this router here is non-client 1, and that this is here non-client 2. So these 2 routers here are non-clients. And this one here is going to be client 1, and let's say that this one here is our client 2. Let's see, from the route reflector's perspective, which routes by default will be advertised where. So let's say that we receive an external route. So when we receive the external route, by default, this route will be advertised to all the external peers. It will be advertised to all non-clients. And interestingly, this client here will advertise it here, but this client will not advertise it to other non-client, and this non-client, and this non-client here will not advertise it to this non-client here. Why? Because these here are just regular IBGP sessions. There is nothing special about them. There is no reflection of the routes. As far as NC1, non-client 1 is concerned, this route received here is just a regular internal route. The route reflector will advertise this to clients, and this client will advertise this to external routes, because from the perspective of client, this is just a regular internal route. It doesn't really need, or doesn't even have, any special configuration in relationship with the route reflector. It's the route reflector that is specially configured in regard to these 2 clients here. So this route will be advertised to all external peers, non-clients, and all the clients. Now let's take a look what's going to happen when we have a non-client route received. So let's say that this non-client 1 receives the route from an external peer 1. By default, it will advertise this to non-client 2, but non-client 2 now sees this as an internal route, so it will not advertise it to the route reflector. Non-client 1, though, sees this as an external route, so it will advertise it to its other internal peer. From the perspective of this router, there is nothing special about the route reflector, and route reflector here will not re-advertise this to a non-client. Why? Because this is a regular internal route as far as route reflector is concerned. It will, however, advertise this to external peers, and also it will advertise it to clients. Now, this is significant because this is an internal route, but because we have relaxed the split horizon rules as far as these routers here go, we have relaxed it not only for the routes received from clients, but also those received from non-clients. We somehow have to get the routes from here to here. So this route will be advertised to clients as well. Now, client 1 will advertise this to our external peer. Let's now take a look what's going to happen with client received route. So let's say that this client here receives a route. It's going to advertise it to the route reflector. Now, route reflector will obviously advertise this route out to its external peers. So this goes to external peers. We expected that. Also, because this is a client, we are relaxing the split horizon rule between our clients and the rest of the internal network. So this route needs to go to the non-clients, so it will be reflected to non-clients. Now, as far as non-client 1 is concerned, this is an internal route, so it won't be advertised to other internal peers, and the same thing happens on non-client 2. Non-client 1 will, however, advertise this to our external peer. Now, route reflector will reflect the client received route not only to non-clients, but somehow we have to get this route all down here. So this route goes here, which means that this route will be reflected to clients as well. So when it comes to the route reflection rules, I have listed them here. Client routes will be reflected to externals, clients and non-clients, and non-client routes will be reflected to external, will actually be advertised. We are not calling this reflected, so I might even cross this, but they will be reflected to clients and non-clients for client received routes, and for non-client received routes, they will be reflected to clients. But they will be advertised to external routers, external peers, because the internally learned routes are always advertised to external peers, as long as they are valid and best. How can we then utilize this to fix our problem? Well, the solution, to me at least, is obvious. We are going to make router 3 a route reflector. Now, we have two possible approaches. We can make R2 a route reflector client and R4 a route reflector client, in effect making both R2 and R4 clients. But that way, I'm not going to show you this behavior with clients and non-clients. This would be the recommended way of doing it, but I'm going to break the rules a little bit, or break the tradition. So I'm going to make R2 here non-client. In other words, I'm not going to configure anything special between R2 and R3, but I am going to make R4 here the route reflector client. So I'm going to configure R3 to reflect the learned routes from R2 to R3. Before I do that, what I'm going to do is, we have the loopback here on R4. We already know we have it because we have the peering between it, between R3 and R4, between those loopbacks. Now I'm going to add this into BGP. What I should be observing there, and I'm going to do this before I configure the route reflection, is that this loopback of R4 is visible in the BGP tables on R4 as a locally generated route, and on R3 as an internal route, which means it will not be advertised to R2. When I configure the route reflection, we should be seeing R1's loopback all the way on R4 and R4's loopback all the way on R1. Let's go ahead and configure this. So I'm going to start with R4, as I said. I'm going to go to router BGP, 65.234 address family, IPv4, and I'm going to say network 192.168.0.4 mask 255.255.255.255. So now, what I should be seeing on R3, if I do show IPBGP summary, I should be seeing from R4 that there is one route that is learned. Let's take a look at that route. So if I do show IPBGP, I should be seeing now from R4 that I'm learning one route, 192.168.0.4, and this is an internal route, which means that if I go to R2, and if I do show IPBGP summary, I'm not going to be seeing anything learned from R3. And here we go again. That's okay. We can fix that easily. Now, if I do show IPBGP, I'm not going to be seeing anything from my R3 router learned on R2. And the reason for that is that that was an internal route on R3. So our R2 here, that is an internal route. So it will not be advertised to R2. Let's fix it. So what I'm going to do on R3, I'm going to go to router BGP 65.234, and remember, configuring route reflection will affect the routes. Hence, it's a policy command. So I need to configure it under the address family. So I'm going to go into the address family IPv4, and I'm going to say neighbor 192.168.0.4, simply route reflector client. That's it. When I press enter, the BGP session is going to go down and it's going to re-establish itself. It's going to go down because we have changed the configuration that deals with the route reflection. Technically speaking, there is really no need for this to go down, but this is what iOS will do. Let's see if there has been any change in behavior. So if I go to R4, if I do show IPBGP summary, I'm going to see now that I am receiving two prefixes from R4. So if I do show IPBGP, look what I'm seeing. I am seeing the loopback of R1, and I'm seeing the loopback of R2. So the routes that I did not receive before, this route here, actually let me do it this way, this route here and this route here were now both advertised to R3 and reflected to R4. One more thing I want to show you before we continue is take a look at the next hop for these two routes. It's 192.168.0.2. So we know that R2 here was configured with the next hop self towards R3, but this was not changed by R3 when it reflected the route. Furthermore, on R2, if I do show IPBGP now, I'm going to be seeing here the loopback of R4, and here it is. I am seeing the loopback of R4. And on R1, if I go here, if I do show IPBGP, I'm going to be seeing the loopback of R4 here as well. So if I ping 192.168.0.4 source loopback 0, I'm going to have the ping all the way there. Route reflectors are a very, very good scalable solution for scaling the number of peerings that you might have in your autonomous system. But they are not the only one. There is another solution called the confederations, the BGP confederations. The idea behind the confederations is to divide the large autonomous system into smaller, more manageable autonomous systems while still presenting the same coherent view of the internal routing to the outside world. In other words, the outside world is not going to see the complexities, is not going to see all the members of the large autonomous system. It's not going to see all the members and the sub-autonomous systems of the confederation. It's going to see one large autonomous system. But inside the confederation, the entire BGP configuration has been divided into smaller, more manageable pieces that we call sub-autonomous systems. These sub-autonomous systems, sometimes called the member autonomous systems or simply members, are really, really small autonomous systems that abide by internal BGP rules. Between the sub-autonomous systems, rules that are very similar to ebgp are in use. Let me explain that. Let's say that we had an autonomous system that consists of, say, 3 routers that have peering sessions that look like this. Now, because these peering sessions are not directly connected, this router here, or we don't have full mesh, this router here is most likely going to be a route reflector. Now, let's say that we have another autonomous system that may look exactly the same. So here we have the route reflector for these peerings, and let's say that we have the peering between these here. Now, we know, let's say that this here is our AS 65001, and let's say that this is 65002. Now, let's say that these belong to the same organization that has the AS 12, for example. So inside, we are using private autonomous systems, but we want to represent this whole big autonomous system to, let's say, our autonomous system 100 here, that may have a full mesh, as AS12. So this router here that peers with this router here is going to think that it is peering with the AS12. So this whole entire autonomous system here is represented to the outside world as a single autonomous system. However, when we go inside these members, we are first of all seeing that we have 2 autonomous systems. So this peering here and this peering here is a regular IBGP peering, which means that routes received from this router by this router will not be advertised to this unless this router is made a route reflector. So first thing that I want you to observe here, the fact that we are using a confederation here does not automatically mean that we are not going to be using route reflectors. We can, if we needed to scale the number of peering sessions inside our sub-autonomous system here. Now, this router here and this router here, they are in the same confederation, but they are in different confederation members. So the peering session between them is going to be something between IBGP and eBGP, and I like to call this CBGP, or the confederation BGP. I'll explain what are the rules there. Now, when these routes are received here, they abide to the same rules that exist here. So here we have regular IBGP sessions. So let's see what's so special about the confederation BGP. First thing, I want you to remember one thing. Remember when we talked about the BGP attributes, and we talked about one that was called the local preference. So if this router here set the local preference, it will not affect only the routers in this sub-autonomous system, they will affect the routes in the entire system here, because the local preference will actually transit the CBGP session. Furthermore, when this router here advertises the route to this router, let's say that we used next hop self, or if we didn't, even worse, this would be by default the next hop here and here. And you know what? Also here, because the next hop will carry over the CBGP. So another thing that will survive the peering session between our sub-autonomous systems is the next hop. So will MED, or the metric. One thing that doesn't exist between these two, or the assumption is that it doesn't exist, is the IGP routing protocol. So the session rules here, let me use a different color here. So when it comes to the session, we need to abide to ebgp rules, which means that the neighbors need to be directly connected. If they are not directly connected, we need to have some routing protocol between them, and we have to configure the ebgp multi-hop. But these values here will be carried over. But what about the AS path? How does the AS path look between these members here? Well, that's very good if you ask yourself that question. Let's go to the next page. So let's say here that we have our AS, what was it? AS 100. And here we have our 2 autonomous systems. So this one is 12, this one is 65002, and this one here is 65001. Now, when the route is advertised from AS 100 to the router that sits in 65002, the AS path is simply going to be 100. Now, when this route gets advertised inside this sub-autonomous system member here, we know that the AS path will not change. Now, when this route goes out to 65,001, our AS path is going to change, but in a very unusual way. We are going to have 100 at the end, and then in parentheses, we are going to have 65,002, which indicates that this was learned from so-called confederation peer. Confederation peer is the router that is in the same confederation, but in a different sub-autonomous system number than we are. Now, let's say that here our AS 65001 had a peering session with a router in, say, AS 200. How will the AS path look when it gets advertised here? Well, it will look like this. It will have 100 and then 12. Because when this route leaves the confederation, we have to actually remove the traces of that confederation. The reason is that entire AS12 is going to represent itself to the rest of the world as one big AS. So from the perspective of AS100 and AS200, what sits between them is AS12. They are completely unaware of the internal complexities that might exist in the AS12. There are some special considerations when it comes to the confederations. First of all, if you are considering using confederations in real life, the initial answer that I have to give you is don't do it. The reason is that confederations are truly designed for special purposes, like mergers and acquisitions and really, really large networks. They are, or I shouldn't say they are, they do require an additional work and additional maintenance, and they do require a little bit more care and attention than route reflectors. Route reflectors are good everyday solution for scaling your BGP peerings. But then again, in some cases, you don't have a choice and you have to go down the confederations. If you have to configure the confederations, keep in mind that all routers must be configured to be aware of the confederation identifier. Now, what I mean by that is when you are configuring your BGP, you have to start, you say router BGP, and then you specify the AS number here. And then here we are going to say BGP confederation identifier, and we are going to specify what is our confederation. Now, this X here is a sub-confederation AS, which means in this case here it would be our 65,001 or 65,002, depending which router we are configuring. And this number Y here is actually the confederation identifier. So it would be our AS12. Another thing that you should configure on all peers. Now here in the slide I say that all routers should be configured to be aware of the confederation peers. What I mean by should and not must is that really this requirement exists only on the routers that are actually peering with other sub-confederations. So this router here and this router here are the two routers that would require this next configuration. And this next configuration is BGP confederation peers, and then you specify the list of peers. So this letter Z here, or this number Z, is actually other sub-confederation members. So we are helping our routers determine which of our neighbors are actually going to follow the sub-confederation rules and which are going to follow the external rules. Because remember, if the AS number is not this, we are by default going to behave as if this was an external peer. However, if the other router is the member of the same confederation, we have to behave slightly differently. We have to behave according to these rules that I described in these previous couple of drawings. So it's very, very important to configure at least these routers, this one here and this one here, to be aware of these peerings. However, as a good common sense practice, I would recommend that you configure the configuration peers on pretty much all of your routers in your configuration.